Hello, welcome to the course of Excelling with Mathematical Modeling. Continuing with our previous lecture on stability analysis, I will now extend it to a system of differential equations, mainly two differential equations. So, let us consider the differential equation of the form dx dt equal to fxy and dy dt equal to gxy. So, if x star y star is the steady state solution, so obviously it is going to satisfy this equation and this equation. So, to find the steady state solution, we have to put dx dt equal to 0 and dy dt equal to 0, which will imply fxy equal to 0 and gxy equal to 0. And if we say that x star y star is our steady state solution, then obviously this is going to satisfy this equation, and hence if you substitute those two values, then obviously g of x star y star and f of x star y star are both equal to 0. We will now finding the condition that when this system of differential equation is stable. So, as defined before, now it is two variables, one is x, another is y. We give a small perturbation about the equilibrium point x star and y star. So, if you do that, you will be getting dx dt, that is equal to f of x plus x star and dy dt equal to g of y plus y star. Now, we will be using the Taylor series expansion, and if you recall, the Taylor series expansion is f x y is equal to f of a b plus x minus a times f x at the point a b plus y minus b times f y at the point a b plus higher order terms. And since we are interested on linear stability analysis, we have only taken the linear terms. So, this was y plus y star, x plus x star. So, this was in the form, let me rewrite them. Dx dt equal to f x y and dy dt in the form g x y. So, I will be using this formula or Taylor series expansion on this. So, if I take the first equation, this will give me dx dt equal to f x star y star plus x minus x star into fx x star y star plus y minus y star into fy x star y star plus higher order terms. In the similar manner, dy dt will give me g x star y star plus x minus x star into gx x star y star plus y minus y star into gy x star y star plus higher order terms. So, we neglect the higher order terms and we put the differential equation. So, from here you can see that if I differentiate dx dt, it will be d capital X dt, as your x star is a constant, and also I can replace x minus x star equal to capital X. So, we will be using these two, and if I substitute here, my dx dt will be d capital X dt. Because x star y star is an equilibrium point, this will be equal to 0, this will be equal to 0 as stated earlier. So, we are left with x minus x star, which is capital X into f x x star y star plus y minus y star is capital Y. So, y times f y x star y star. Similarly, dy dt equal to capital X g x x star y star plus capital Y g y x star y star. Now, this can be put in the matrix form also. So, if I write it in the matrix form, then dx dt equal to some a x, where my x is x y and a is f x f y g x g y at the point x star y star. Now, let x equal to some v hat e to the power lambda t, where your v hat not equal to 0 be a trial solution. So, I am going to substitute it here. So, dx dt will give me v hat e to the power lambda t. So, if I substitute it here, what I get is v hat lambda e to the power lambda t equal to a v hat e to the power lambda t. Now, clearly e to the power lambda t is not equal to 0, means we can write this as a v hat minus lambda v hat into e to the power lambda t equal to 0. This part is not equal to 0 and hence, or 0 matrix, and hence I get a v hat equal to lambda v hat. If you recall, this is just the definition of the eigenvalue. So, basically this lambda here is the eigenvalue of this matrix capital A. Now, to find this eigenvalue, what we do? We take this to the left hand side and you take the determinant of that, which will give us f x minus lambda f y g x g y minus lambda equal to 0. So, this is the matrix. You minus lambda I from here, because this can be written as determinant of A minus lambda I into V hat equal to the null matrix, and then you take the determinant and from there you will get this. If you simplify this, then you get it is as lambda square minus f x plus g y into lambda plus f x g y minus g x f y equal to 0. Now, if you see this one, it is just the addition of off diagonal, which is known as the trace of the matrix A, and this is just the product of A if A has been the determinant. So, this is basically determinant A. Now, for the system to be stable, both the eigenvalues needs to be negative, and if both the eigenvalues need to be negative, so then sum of the eigenvalues, that is trace A, must be, because if lambda 1 and lambda 2 are the eigenvalues, this generally gives the sum of the roots and this gives the product of the roots. So, the sum of the roots, if both lambda 1 and lambda 2 are negative, must be less than 0, which implies that the trace A must be less than 0, and if lambda 1 and lambda 2 are negative, their product must be positive, which implies that the determinant A must be greater than 0. So, the condition that the system of two equations will be stable is that the trace of this matrix A must be less than 0 and the determinant of this matrix A is greater than 0. You can remember them as a formula also, or you can straight away derive, because anyway you have to find this matrix A and find the eigenvalues. If you can straight away find the eigenvalues, just see whether both of them are negative or not. If both of them are negative, then your system is stable. If it is not, that means if one of them is negative, one of them is positive, or both are positive, in either cases the system is unstable. Now, this criteria or this condition is known as Routh-Hurwitz criteria. So, for two equations, if your characteristic equation is of the form plus a1 lambda plus a2 equal to 0, then the condition that the system is stable is a1 is positive and a2 is positive. Please note that this equation and this equation is a tiny difference is of this negative sign. So, if I bring this negative sign inside, then I put a positive sign here, this negative sign is absorbed in this a1, and hence here a1 is positive, a2 is positive. So, either you write this equation as a negative one or you write it in the positive one, then this is easy to remember. If the equation is suppose 3, then you get a cubic characteristic equation, then it is a1 lambda square plus a2 lambda plus a3 equal to 0. This is for stable. In this case, the Routh-Hurwitz criteria that the system will be stable is a1 positive, a2 positive, a3 positive, and with that a1, a2 minus a3 must be positive. So, if all these three conditions or 4 conditions are satisfied, we say the system is stable. So, let us move on to some example. So, you have to find the stability of the system dx dt equal to minus x plus y and dy dt equal to x y minus 1. So, the first thing is you have to find the point of equilibrium, and to do that you put dx dt equal to 0 and dy dt equal to 0. This gives you minus x plus y equal to 0 implies x equal to y, and this gives you x y minus 1 equal to 0, which implies since x equal to y, I replace y by x minus 1 equal to 0, or x square equal to 1 and x equal to plus minus 1. So, we have x equal to plus minus 1. So, when, which we got from this equation. So, when x equal to 1, we put that here, y is also 1, and when x equal to minus 1, y is also minus 1. So, we get that minus 1 and 1 1 to be the steady state solution. So, once you get the steady state solution, now you calculate that matrix A. So, the matrix A is you take this as F and take this as G. So, A matrix del F del x, so minus 1, del F del y plus 1, then del F del x, sorry, del G del x, which is y, and del G del y, which is x. And this is at that point x star and y star. So, one of the set is minus 1, another set is plus 1, plus 1. So, now we have to calculate the eigenvalues. So, for 1 1. So, we see for 1 1 you are getting a minus lambda I equal to 0. This will give you minus 1 minus lambda 1 because x and y is 1. So, this is 1, this is 1 minus lambda, and this is equal to 0. So, if I solve this, this is lambda plus 1, this is lambda minus 1, lambda plus 1 into lambda minus 1 equal to 0. So, I get lambda square minus 2 equal to 0 and lambda equal to plus minus root 2. So, one of the eigenvalue is positive, another eigenvalue is negative, implies the system is unstable. At this point, I must notify you that there are other classifications also, which we will be coming in my next lectures. For the time being, you just need to know whether the eigenvalues are negative or positive. If both of them are negative, then the system is stable. If that criteria is not satisfied, that is, if one of them is stable, is positive, another is negative, or both are positive, then the system is unstable. Let us check what happens for a minus 1 and minus 1. So, in that case, your A value will be minus 1 1 minus 1 minus 1, and your A minus lambda I, which will be minus 1 minus 1 minus lambda 1 minus 1 minus 1 minus lambda, and this is equal to 0. So, we have lambda plus 1 whole square plus 1 equal to 0. So, in that case, you get lambda plus 1 square equal to minus 1, we write this as I square, and your lambda is minus 1 plus minus I. So, I specifically choose this example to show that if what happens when the value of lambda is imaginary. In that particular case, you have to look at the real part. So, if the real part is negative, then your system is stable. If your real part is positive, then your system is unstable. So, in that particular case, the system is stable at the point minus 1 1. And as I told you before, we have more classifications on this stability, and which we will be learning later. Let us take another example where we introduce the parameters alpha, beta, gamma and delta and k. And how do you check the stability of this particular example? So, what we generally do is you put x equal to x plus x star and y equal to y plus y star, and then you retain only the first order terms and you ignore the higher order terms. So, if I use that, then I will substitute it here. I will get d dt of x plus x star equal to alpha times x plus x star 1 minus x plus x star divided by k minus beta times x plus x star y plus y star. Now, why we are doing this? Because I want to show that by using this method and by using the formula which we just derived, we both get the same answer. So, you just remember any one of them. The previous one is will take less time, this will take more time, but this is for the sake of the understanding. So, here x star and y star are the equilibrium points and it is also a constant. So, in this particular case it is dx dt. I multiply this whole term, this is alpha x plus alpha x star, then minus alpha by k, then x square plus x star square plus 2x star into x. So, I multiply this multiplied by this and this multiplied by this, minus beta times x y plus x star y plus y star x plus x star y star. Now, let us retain only the first order terms and I will ignore or discard the second order terms. So, here it is alpha x. This is just a constant, but I just write x star. This is the second order we ignore. So, minus alpha by k x star square minus 2 alpha by k x star into capital X minus second order term we ignore beta x star into y minus beta y star into x minus beta x star y star. So, let me write the constant term first. So, from this 2, if I take alpha x star common, I get 1 minus x star by k, and then this minus beta x star y star. Then I take x common from this, and this, and you get plus alpha minus 2 alpha by k x star minus beta y star into x minus beta x star into y, this part. So, now if you look into this term, this is nothing but this term where you put x equal to x star and y equal to y star. And since x star y star is the equilibrium solution, obviously this is going to be 0, and hence this term is equal to 0. So, you are left with this and this. Now, let us simplify the second equation. So, for the dx dt, you are left with alpha minus 2 alpha x star by k minus beta y star into x minus beta x star into y. If I now take dy dt, which was minus gamma y plus delta times xy. So, you put x equal to x plus x star, y equal to y plus I star like before. So, this will be dy dt minus y. So, y plus y star plus delta x plus x star y plus y star. So, I simplify minus gamma y star plus delta x y plus delta x star capital Y plus delta y star capital X plus delta x star y star. And if you write this in the form minus gamma y star plus delta x star y star, constants, this we ignore because it's a second degree term, plus delta y star into x plus delta x star minus gamma into y. So, we have x term, we have y term, and we have the constants. So, with the same logic, if x star y star is our equilibrium solution, it is going to satisfy this. So, if I put an x star here, y star here, this is going to be 0, and hence this part is equal to 0. And we are left with dy dt is equal to delta y star into x plus delta x star minus gamma into y. So, this is our linearized form, and if we want to construct the matrix A from here, it will be alpha minus 2 alpha x star into x minus beta y star. This is minus beta x star, this is delta y star, and this is delta x star minus gamma. So, we just take the components from here, coefficients, and we put it here. Now, what I am trying to show you here is that we have the original equation dx dt is equal to alpha x 1 minus x by k minus beta xy, and dy dt is equal to minus gamma y plus delta xy. And our previous derived formula says that you take this to be some fxy, this to be some gxy, and our matrix A will be fx, fy, gx and gy at the point x star y star. So, if I find fx from here, that will give me alpha minus 2 alpha x by k minus beta y. If I differentiate it with respect to x, if I differentiate it with respect to y, it is just minus beta x. Differentiate this with respect to x, you get delta y, and with respect to y, it is minus gamma plus delta x. And this need to be calculated at x star y star. So, I just put x star and y star here, and you can see that both these matrices are same. So, whether you use this method or whether you use previous method, you get the same answer, but then this is time saving. So, we use this. So, you now calculated the matrix A, we now have to look into the stability of the system, and for that you need to find the equilibrium solution. So, to find the equilibrium solution, you have to put dx dt equal to 0, which is alpha x 1 minus x by k minus beta xy, and dy dt equal to minus gamma y plus delta xy. So, you put this equal to 0, you put this equal to 0. So, from this equation you get y minus gamma plus delta x equal to 0, which implies y equal to 0 and x equal to gamma by delta. So, if you put y equal to 0 here in this particular equation, you get alpha x 1 minus x by k equal to 0. So, this will imply x is 0 and x is k. So, for y equal to 0, you get two values of x, hence 0, 0 and k 0 is your steady state solution. Now, you substitute x equal to gamma by delta here. So, if you do that, you get alpha gamma by delta 1 minus gamma by delta k minus beta again x gamma by delta times y star, which I need to find. This is the common part which goes off, and you are left with y star equal to alpha delta k minus gamma by delta k multiplied divided by beta. So, alpha by beta k delta minus gamma divided by delta k. So, another non-zero equilibrium solution is when your x is gamma by delta, your y value is alpha by beta delta k minus gamma by delta k. So, you need to find the equilibrium solution at all these points. Now, before that, if this equation represents a population, in that particular case, all the solutions has to be positive. So, we have to assume that all the parameters are positive, that is alpha, beta, gamma, delta, alpha, beta, gamma, delta and k, they are all positive, and at the same time the equilibrium solution is positive. So, this is k 0, this is 0 0, and here when it comes, so this is positive, for this has to be positive, this part has to be greater than 0. So, the condition that the non-zero equilibrium point will exist if we consider this as a population, then it is lambda k minus gamma has to be greater than 0. So, the point is, when you have the equation with parameters, you will see that either it is satisfying directly or you will get some condition for which need to be satisfied for finding the positive equilibrium solution and also for the stability of the system. Now, let us look into the stability of the system say at the point k 0. So, if you want at the point k 0, then you find what is your matrix A, which was alpha minus 2 alpha x star by k minus beta y star, then minus beta x star. Here it is with respect to x, so delta y, and with respect to y, so minus gamma plus delta x. So, if we want to find at the point k 0, so I have to substitute x star equal to k and y star equal to 0, and your matrix A will be alpha minus 2 alpha k by k minus 0 minus beta k, this is 0, and minus gamma plus delta k. So, if I simplify, I get this to be minus alpha minus beta k, this is 0, it is delta k minus gamma. If I want to find the eigenvalue, then it is mod A minus lambda I equal to 0, which will give me minus alpha minus lambda minus beta k 0, delta k minus gamma minus lambda equal to 0. So, from here I get lambda plus alpha, and this is lambda minus delta k minus gamma equal to 0. So, one of the value you can see lambda equal to minus alpha, and another value is lambda equal to delta k minus gamma. This is clearly negative because alpha is a positive constant, but this, because of the existence of equilibrium, positive equilibrium, this is positive. So, one of the lambda is, one of the eigenvalue is negative, one of the eigenvalue is positive. So, at k 0 system is unstable. Similarly, you can check for 0 0 and this non-zero equilibrium point, which I leave for practice for you. In my next class, I will be again discussing about the stability of the system, but Lyapunov stability. Till then, bye bye.